So what I want you to remember from this is that if we just had a ramp, back when we did simply ramp problems and we found the acceleration of an object sliding down a ramp, the acceleration was just g sine theta. Now it's 5/7 g sine theta for a sphere rolling down a ramp. This goes with what we said. The acceleration is now less. Okay? The acceleration is now smaller than it was when an object just slid down. In other words, it picks up less speed. And one of the ways you can rationalize this is the reason it picks up less speed is because not only does the object have to make it down to the ground, not only does it have to pick up speed to make it down to the ground, it also has to rotate. And because of this, because it has to rotate, the acceleration is going to end up being a little bit less than it was before. There doesn't have to be, there isn't as much acceleration, which means there's not going to be that much, or as much linear speed. Definitely makes sense, totally makes sense. That it's not going to be moving quite as fast. Some of that kinetic energy that we talked about earlier is now wrapped up in rotational kinetic energy, meaning the translational kinetic energy just isn't going to be as much. Now another related question you might get asked is, what is the minimum coefficient of friction that would allow this to roll smoothly? Minimum mu. Now what this would mean is, what's the smallest coefficient of friction that would allow smooth rotation, smooth rolling? What this is really asking is, what is the max, you have to think in your head, if we're talking about the minimum coefficient of friction, the minimum coefficient of static friction that would allow this to happen, that would mean that the force of friction is at its maximum. Okay, you should be used to this. The minimum coefficient of static friction, if we're looking for that, what that really means is, hey, if static friction is as big as it can possibly get, then what happens? So, we're looking really for max force of friction. And the nice thing is, if we're looking for the maximum force of friction, let's go back to our F net equation in the x direction. Fg sine theta minus Ff equals max. Before I forget, let me just write this in. Compare to ax equals g sine theta for sliding. Okay. If I'm looking for if I know that the condition is minimum mu, that means I can use the maximum force of static friction. And I know an equation for that. I know that that's mu Fn. Okay, so here's the acceleration. If this acceleration happens to cause the maximum possible force of static friction, I can plug the 5/7 g sine theta in here. I also know the normal force. I found it up here is mg cosine theta minus mu mg cosine theta equals m times 5/7 g sine theta. Oh boy, lots of stuff going on here. I have an m and a g in every single term. They will all cancel out, leaving me with sine theta minus mu cosine theta equals 5/7 sine theta. I'm looking for mu. So what that means is I need to subtract sine theta to the other side. This is really 7/7 sine theta, so 5/7 minus 7/7 would give me a negative 2/7 sine theta. I have negative, negative, so that will cancel. I divide both sides by cosine of theta. I get that the minimum coefficient that will allow smooth rotation, smooth rolling, is 2/7 tan theta. Is that what I got? That is what I got. Excellent. Okay? If the coefficient isn't at least, if this is the minimum coefficient, if the coefficient is smaller than this, What that basically means is friction is not enough to keep this from sliding as it also rotates. There will be kinetic friction, sure, okay? There will be some rotation, but it will also slide as it rotates. Oh, and I guess I keep missing stuff that I want to write and talk about. I guess back to what we found first. Since AX, okay, this is going back to this part. Since AX is less, object does not accelerate as fast so it has a slower speed at the bottom. And again, this agrees with what we found earlier. It agrees with what we found earlier in terms of splitting the kinetic energy into rotational and translational. Causing a lower velocity. I know it's a lot of writing. You will see a bunch of problems like this. Objects rolling on a ramp. Again, it's very similar to the problem we were working last night. The forces, you still need net force equations. We're just also adding in the fact that this is rolling, so there must be some sort of torque. It is rotating. Okay. Again, there's not a ton of ways that they can ask these questions. They might put different objects up here. Matter of fact, that's going to be our tutorial, seeing how different objects respond to rolling down, seeing if there's any differences. But the basics are all the same, okay? Free body diagram, net force equations, net torque equations, combine things, compare the accelerations, okay? Matter of fact, that's what we're going to talk about now, is what happens if we put different objects on the ramp. Different objects on the ramp. And the thing with different objects is they will have different moments of inertia. And these different moments of inertia will actually cause different energies and different speeds to be gained. So I am going to switch up one little piece of notation just because we're going to be talking about accelerations now. So before I was using the coefficient I equals a mr squared, and a was just a coefficient. I'm just going to change it to b right now, so no one, so we don't get confused as to which a we're talking about. B mr squared, where b is a coefficient. All right. So from before, we saw that the torque, the net torque in an object rolling down a ramp, was caused by the force of friction, and we know net torque equals I alpha. Doing some substitution, we know that this is R F, the actual force, times the sine. We know this ends up being 1. We know this ends up being the radius of the object. We know that the moment of inertia is b, the coefficient mr squared, times the acceleration of the object, the linear acceleration, you can say ax, over r. So we know this ends up being, let's see, r times the force of friction we found earlier, the general one. This is all from up above, mg sine theta minus max equals b m r squared times ax all over r. We can cancel out r's here, cancel out these r's, we can even cancel out these m's. And what we will find, we get g sine theta minus ax equals b ax. I add the ax to the other side, I get ax plus b ax. I'm going to pull an ax out of both those terms. G sine theta equals ax over, or times 1 plus b. I bring that to the other side, I get, let's see here, g sine theta over 1 plus b is equal to ax. Alright, got a few more minutes, good. So, here's what this tells us. If we increase b was the coefficient back here with the moments of inertia. If we increase b, the moment of inertia increases. So increase b leads to an increase in the moment of inertia. And what we saw is that this also leads to a smaller acceleration. And what that leads to, if the acceleration is less, then there's going to be less speed at any given point because it's not accelerating as much. And if there's less speed, that means there is less kinetic energy at any given point. I guess I should say less translational speed. Okay? There's less translational speed at any point. So, you get an object with a bigger moment of inertia, it's harder to get that object to rotate, so that object will not move as fast. This is different from what we did before. This is much, much different than what we did previously when we said, okay, we have an object up at the top of a ramp, and it slides to the bottom, what's the speed? We just use conservation of energy if the object just slid to the bottom. If the object rolls to the bottom, though, the shape of the object will actually affect how fast it moves. Okay? This is different from what you have done before. This is really interesting. The bigger the moment of inertia, the slower it will move, the less translational kinetic energy it will move. It'll have a bigger share of rotational kinetic energy, I guess you could say, because it's harder to get that object to rotate. More energy has to go into rotating the object. So, you can put that away. The next sheet is the one that I said I didn't give to you. Somehow it got left off or it got covered up. It looks like this. Let me pull it up on the computer. It's not on there yet. Okay, rolling comparison on ramps. This is what I really wanted to get to with this. Okay? So let's say you are doing a lab experiment to determine which type of object will have the farthest horizontal displacement from the edge of the table if it were to follow the track shown below. Now this is actually a question, I believe I used it on a midterm, or some midterm at some point. You have a ramp up here. Imagine we put a ramp on one of those tables, okay? We allowed the object to slide or roll down the ramp. There's a little horizontal spot and then it goes, okay? We want to figure out how fast it goes, or basically how far away it ends up. You have the following objects available to use. You have a wooden block of mass m that slides down the ramp with no friction. You have a ball of mass m and radius r that slides down the ramp with no friction instead of rolling. You have a ball of mass m and radius r that rolls without slipping or skidding down the ramp. You have a hollow cylinder of mass m and radius r that slides with no friction instead of rolling. And you have a hollow cylinder of mass m and radius r that rolls without slipping or skidding down the ramp. So we have 3 and 5 roll, and 1, 2, and 4 slide. And it turns out that actually makes a difference in terms of where they will land and how fast they will move. And they're different shapes, okay? Now, you have a student in your lab group hypothesizes that objects 1, 2, and 4, the sliding objects, will ultimately travel equally far since they don't roll, while objects 3 and 5, while traveling the same distance as each other, will not travel as far as 1, 2, and 4 since they do roll. Your first task is to explain which parts, if any, of the student's reasoning are correct, which parts, if any, of the student's reasoning are incorrect. Now let's talk about this first, okay? The student is majority correct here. Almost everything they said is correct. The objects that do not roll will go farther. The reason they will go farther is because all of their kinetic energy is purely translational. They're not, the rotational part of the kinetic energy, well, there is none if they're sliding. Okay, these objects are simply just sliding down, they're not rolling. What that means is the linear speed is as big as it can possibly be. We don't have to take some of that translational kinetic energy and put it towards rotation. None of the energy is wrapped up in making this rotate. So 1, 2, and 4, because they don't rotate, because they don't roll, will end up having all of their kinetic energy be translational, which means their linear speed will be as high as possible. And their linear speed, because it's as high as possible, will lead to a very high speed here. Obviously, they're all going to take the same amount of time to fall the distance h. So if you let a really big speed here, and they're all falling for the same time, it will go the farthest. Okay? The ones that roll, they're not going to have as high of a linear speed because they're also going to have an angular speed, an angular velocity because they're rotating. And as they rotate, they're not going to get as big of a linear speed here. They will have a smaller speed here, still going to take the same time to fall. They will not go quite as far. So, let's get that part done first. The student is correct that objects 1, 2, and 4 will travel equally as far since